Hello, this is David Maxwell again, back with part 2 of Single Cell Gauging 101. Now we're going to talk about the classic fuel gauging approaches and what you might try to do if you were thinking of rolling your own fuel gauge. One of the goals of having a fuel gauge is to fully use every last bit of energy in your battery. And there are two things working against you here, generally. The first one is the charging voltage tolerance, because every charger is not going to exactly charge it all the way up to the tip top. And then you also have, at the bottom end, as you discharge, shutting down too early. And many people, when they design a system with a fuel gauge, they might try to guard band a little too much because either they don't trust their gauge or they want to try and compensate for different temperatures or different ages of batteries. So they're going to end up shutting down too early, and they're leaving energy on the table that could give their product longer runtime. This often means that you're using 80 to 90% of what's actually available in your battery, and you might be guard banding too much on a new battery just to cover the case for an old or a cold battery, which means for that new room temperature battery, you're going to be shutting down early. So this is how we make the claim that a high accuracy gas gauge can increase the battery runtime. It's not putting energy into your battery or making your system more efficient. It's just allowing you to use everything that's available to you. Since we're talking about single cell fuel gauges, I'm going to show a couple slides that show where the gauge might be placed. Now in your notebook, it's not a single cell, it's usually 3 or 4 cells in series, but you're probably going to have the gas gauge inside your notebook PC battery in a similar fashion as this. So inside the gray box, we have the gas gauge connected, measuring the cell voltage. It's integrating the current through this sense resistor. It might be just a few milliohms, and also monitoring the temperature, and it's reporting all the information back to your application processor. Could be over a 2-wire communication if you have 2 pins on your battery pack for it, like I2C, or a single wire communication like HDQ, for example. But many single cell systems are trying to use the gas gauge on the system side because they want to use a dumb battery pack. And so this could be user replaceable, and the gauge has a lot of extra challenges presented when the battery pack can be swapped in and out. It doesn't know how old this battery is when it's first introduced to this battery. It doesn't know a lot of things. But there is one benefit that you can get besides the communication, you can also have some interrupt pins as well. Actually, that feature is also available on our packside gauges as well, that if you want to bring out extra pins from your battery, that you can have some interrupts to allow the host to go into a low power state and let the gauge wake it up when something important is happening. But these are the basic views of where your gauge could be placed. But whether it's in the pack or in the system on the same PCB as your application processor, it's still going to use the same gauging fundamentals. And it's still going to serve the same purpose as well. It's basically the communication between the battery and user. And I mentioned on the previous slide that the 3 inputs to the gauging algorithm are going to be the battery voltage, the current, whether it's charging or discharging, and the temperature of the battery. In part 1, we talked about how the temperature really affects the internal impedance of your battery and can have a dramatic impact on the runtime available. So the gauge needs to measure the battery temperature very accurately. You don't want it to be measuring the temperature of your charger or the temperature of some very hot component inside your system. So if at all possible, try to let it measure the thermistor that's inside the battery pack. So these are the inputs to the algorithm, and the final outputs, the things you might want to read from the gauge, are things like your runtime, remaining capacity in milliamp hours or milliwatt hours, and also battery health information. If you have a gauge that is learning the battery over time, then it can tell you, compared to when this battery was new, I only have, for example, 80% of the original capacity. Maybe you want to replace it or give the user a warning. So it's nice to have a numerical value to give them instead of them just getting the feeling that this battery isn't as good as it used to be. And then all the information that the gauge can provide can be used by the system to make a lot of decisions about power management. For example, does it want to disable the flash at a certain low value of capacity, or does it want to switch into low power mode? Is it time to start shutting down and run on reserve battery capacity? So if you think about how to implement a fuel gauge, there are three basic techniques. We'll start with the simplest one, and in this part 2 video, we're going to talk about voltage-based and Coulomb counting. And in part 3, we'll get into impedance track. Voltage-based is the simplest one and could be appropriate actually for some applications. Coulomb counting is a little bit more complex and is a pretty popular one because it can handle more conditions than voltage-based. And then impedance track combines the benefits of those and adds a few unique twists to give you all the advantages of those with none of the disadvantages of those two approaches. So if you think about just using a voltmeter to measure a battery voltage, this kind of approach was used on old feature phones, for example. If you can imagine where as the battery voltage goes down, you have, let's say, 4 LEDs, it goes to 3 LEDs. The voltage continues decreasing. Now we have 2 LEDs, 1 LED, and then you get to empty. But the problem with this is that when you have any kind of load, any significant load, your battery voltage is going to be dropping. So if your load is varying, your voltage is varying, and your LEDs are going to be bumping up and down. So that's going to be confusing to the user if that's really happening. Maybe you had the experience with some old phones where you'd be on a phone call with someone and then it said, oh, I only have 1 bar left and I got to get off the phone with you, sorry. And then you hang up and then it jumps back up to 2 or 3 bars. And maybe you say, okay, I didn't really want to talk to them anymore anyway. But for the cases where it really matters, that's going to be confusing, and it's basically going to mean you don't trust what it says and you're going to have to use your own judgment instead of relying on accurate reporting from the system. So as long as the current is very low relative to the size of the battery, this IR drop is going to be very minimal. So you might be able to trust this kind of approach. But if you do have any significant current, the resistance of the battery is going to have a big impact. And as we talked about in part 1, that resistance is highly variable depending on temperature, aging, and the state of charge. In case you didn't watch part 1, here's a slide just to remind you that the impedance or resistance of your battery is a function of those things, and that as it ages, it can easily double after 100 cycles. And even if you're trying to model it and compensate for that resistance in your voltage measurements, you're still going to have variation from cell to cell and from manufacturer to manufacturer. Another slide we showed in part 1, maybe it'll make a little more sense now, is how it varies with state of charge. Full battery has a low resistance, empty battery has a high resistance. Also, room temperature battery, blue or green, has a pretty low resistance, but as it gets colder, the red line, the impedance goes up a lot. So that means as the temperature changes, your voltage is also going to change if you're under load. And this slide again illustrates the differences from within the same manufacturer. If you look at the low frequency impedance, you're going to have a big variation, but within this range. But the second manufacturer could have a variation in a completely different range. So if you try to say, okay, I'm going to measure the voltage, and I know there's a resistance, and I'm going to measure my current and try to calculate what the unloaded voltage would be, well, you're going to have a challenge because you don't know what resistance to apply to that voltage compensation. You also have the challenge of the fact that the battery is really modeled more accurately by a complex circuit like this, and it has a transient response. So let's look at that. The transient response means when you initially apply a load, let's say this is a relatively fully charged battery, it's starting at about 3.9 volts. When you apply the load, it doesn't just drop down immediately to that IR drop as if it were a simple resistor. It will have some very quick drop and then will taper over time until the resistance is fully saturated, and then it will go in sort of a relatively straight line to empty. Same thing happens when you remove the load, then it's going to take some time to relax up. It's kind of like a pillow that you lay your head on, a down pillow, and when you put your head on it, it will take some time for it to compress and get to a steady state. And then when you remove your head, the air will go back into the down filling of the pillow and it will take some time to inflate back up. Same thing happens, in fact, when you charge. It's kind of like pumping air into that pillow. When you remove the charge current or you remove the air you're pushing into that pillow, it's going to deflate to its resting position again. What this means is that when you measure the voltage, you could say, fine, I know that the voltage is going to change with current and temperature and aging, but I'm just going to measure the voltage when there's no current flowing, and I'll use that to report to my user how much is available. Well, then you have to be very careful not to measure here. There's no current flowing, but the voltage has not yet reached a steady state, and you can see that it takes many, many minutes, sometimes even an hour or more, for the voltage to stabilize. And so you need to be able to detect when it's stable, and can you really afford to wait an hour or more for the stable voltage. Even a few millivolts error on the measurement voltage in the flat region of this lithium-ion curve can result in a big difference in the reported SOC, as we'll show in a few slides. Also, this relaxation time is affected by temperature as well as by the state of charge. So this battery is much closer to empty, starting at 3.3 volts. And even with a very short load, when you remove it, it can still take a long time to relax. So the things that impact your relaxation time are how fully charged you are, or your state of charge, the temperature, the duration of the load, as well as the magnitude of the load. So in the previous example, we saw, what if you have a plus or minus 20 millivolt difference? If you measure that voltage too early, before it was fully relaxed, you might be measuring 20 millivolts less than the actual voltage after it finally comes to a steady state. How does that impact your gauging accuracy? So on this plot on the left, let's read it backwards here. If you're fully charged at 100% here, and this is your cell voltage, the red line is how you would map the actual voltage to the state of charge. But if you put an envelope of plus or minus 20 millivolts using the blue and the green curves, how would that map to error in calculation of your state of charge? So if you said, I measured 3.8 volts, for example, if it was really relaxed, that might map to exactly 50% state of charge. But if it wasn't relaxed and you measured 3.8 volts, you might be on the green curve and you might measure 45% state of charge. So let's map that onto this error plot over here. So from full on the right to empty on the left, you can have positive or negative error depending on whether you're overestimating or underestimating the state of charge. So you can see in the middle the error peaks. There's the biggest difference between the curves here because that's in the flat region of the lithium-ion voltage curve. At the ends where it's very steep, the voltage measurement error isn't as important, but in the middle you're going to have the big error, and you can see the peak reaches about 15% in this example. Well, many fuel gauges and many ICs may not even be able to measure more accurately than 20 millivolts. So that's going to add even more uncertainty to your gauging accuracy on top of this relaxation error if they're not handling the relaxation properly. So we mentioned the relaxation error in the previous slide. You also have cell-to-cell variation if you're trying to compensate for the IR drop during load. And if you add up those two components for a new cell, you can easily exceed 15% error. And then as you go to an aged battery, if you're still using your model, which was applicable to a new cell, but you're applying it to an aged battery with higher impedance, then your error just goes through the roof. And as you get towards the end, where the impedance really gets very high, you can see that your total error after a number of cycles is just getting completely unacceptable. So the big challenge that we keep mentioning is the resistance of the battery and how to know what it is and how to use the accurate resistance for your simulations and predictions in the fuel gauging. There are some cases where you might want to use a voltage-based fuel gauge, and it does have some advantages. Learning can occur without a full discharge, meaning after the battery is aged, you don't really care what the impedance is or what the capacity is. All you're going to get from this gauge is a relative state of charge. It's just going to tell you percent. It's 75% state of charge, for example. It doesn't tell you how many milliamp hours you have, but you can know whether it's an old battery or a new battery, it's 75%. It might be 75% of 1,000 milliamp hours. If it were a new battery, it might be 75% of 800 milliamp hours if it was an old battery. But it's still relative, and it's correct in that it can still tell you 75%. Another factor we didn't mention, but I'll briefly talk about here, is the self-discharge. When you set your battery on the shelf, the chemical reaction is slowly going to occur inside, and it's going to lose energy slowly over time just sitting there on the shelf or in the warehouse or in the shipping container. And so it doesn't need to have any correction for that self-discharge because it's just measuring the voltage, and as the voltage slowly goes down, as the chemistry is self-discharging, it's going to automatically compensate for that because you're just looking directly at the voltage. And so application where this might be fine is as long as you have a small load current relative to your battery capacity. The IR drop will be insignificant, and you can still have accurate gauging using this method. But if you have any kind of load current, or if it gets very cold, even with a small load current, the battery impedance is going to cause this gauging algorithm to be very inaccurate. And we saw that impedance, being a function of temperature, aging, and state of charge, is highly unpredictable, and so that's going to cause the error to be unpredictable if you use a voltage-based fuel gauge. Let's move on to the second classic method for implementing a fuel gauge, and that's called Coulomb counting. And this is basically where you integrate the current, and that's where you get the name Coulomb counting. So if you start from a fully charged battery and you integrate the current as you're going down, you should be able to know how much charge has passed and how much charge is remaining, assuming you know what is your Qmax. So if you integrate this one, for example, you have just over 5 amp hours of capacity. But we saw that usable capacity really depends on your IR drop, and so it depends on your current and it depends on your resistance, which can be changing over time. So most of the Coulomb counting gauges will adjust the Coulomb count depending on the temperature, depending on the load rate, and try to estimate when it's going to hit the wall. But you don't want to wait till you get to 0% and then if you had some error, suddenly jump to 0%. You don't want to run into that wall and break your nose. So most Coulomb counting gauges will have some EDV1 and EDV2 points where it can synchronize and say, I'm getting close to the wall, and if I was reporting 10% right here, once I reach this voltage, I'm going to jump to 7% so that I can get a little more accurate before I hit the next point and the next fully empty point. But if you use a fixed voltage for these, and you can do this by characterizing your battery if you have a number of battery voltage curves under different temperatures and different loads, you can set these points and figure out where to adjust your Coulomb counting. But there's a problem if you use fixed voltages. And so the solution to that is to use variable voltage. So let's imagine if this is your 7% synchronization point, what if you have a bigger IR drop for some reason? That means you're really going to, when you hit that voltage, it's going to be much earlier, and you still have 30% remaining. If you were on this curve, you would have 7% remaining at that voltage, but on this curve, you have 30% remaining until you hit your EDV. So that you don't want to jump down to 7% and tell the user 7% when you really have 30%. So you need to have a way to compensate that EDV voltage, which is where we come up with the next generation of Coulomb counting, and we call it CEDV. So knowing the current voltage, the current temperature, and the current load, we can adjust that 7% synchronization point. And for this curve, it would really be here that you have 7% until your terminate voltage. But again, this can all be modeled pretty well for a new battery, but that IR drop is going to change for an aged battery. And so that's where this algorithm is going to have big problems. Coulomb counting can overcome some of the problems that we saw with voltage-based gauging. The transient response of the battery, the distortions on the voltage measurement are not going to impact your gauging if you're just looking at the current only. And you can get pretty high accuracy because current integration hardware is very good now. So if you have a Coulomb counter, basically an integrating ADC, then you can have good tracking of the coulombs in and out of your battery. But typically you're probably still looking at 3 to 10% error depending on how wide your operating conditions range and how the load ranges as well. And it's only going to get worse again with aging. Another disadvantage of this is that you need a learning cycle to update Qmax. We showed in previous slides that the chemical capacity is reducing as you cycle the battery, perhaps 3 to 5% after 100 cycles. So if the capacity is shrinking, you need to update that so you can give more accurate predictions. So every once in a while, you're going to need to go from full to almost empty. Most gauges don't require you to go all the way to empty, but you'll need to get almost empty. And so some systems and some users may never actually do that, may not allow a learning cycle. And so your error is going to increase if you continue cycling and the Qmax is reducing, but you don't let the gauge have a chance to learn it. The problem we mentioned before of self-discharge does affect Coulomb counting as well, because if the energy is being lost inside the cell through a chemical reaction, it's not energy that you can detect passing through the sense resistor, so the Coulomb counting gauge is not going to know that energy is being lost internal to the cell. So you can try to model it and just use a clock and say automatically reduce capacity by X amount every day, but that's not going to be accurate because the self-discharge is again a function of temperature, it's a function of age of the battery, it's a function of state of charge. So it's going to happen at a different rate for every battery and under different conditions. And again, your compensation is going to be based on resistance, but that resistance is a highly variable function. And so it causes the same problem for voltage-based gauging and for Coulomb counting gauging. So we saw where each of these techniques can shine. You can get a very accurate gauging using an open circuit voltage or a relaxed battery voltage when you have no load. That's the voltage-based method. And when you have a load, then Coulomb counting can track how much went in and how much went out. But they each have their problems as well. So the voltage-based gauge, when you have that IR drop, it's going to affect your voltage measurement, which is going to affect your state of charge prediction. And that IR drop is a complex function depending on these factors. Current integration is also affected by the resistance of your battery, which is changing over time, temperature and state of charge. And so in the next part, we're going to talk about how impedance track can handle these two problems and how it can overcome them and give you the most accurate fuel gauge algorithm that there is.